Welcome back. We're now going to start talking about data structures. We have the language now to talk about efficiency of algorithms, big O notation, and we've seen that play out with searching and sorting algorithms. And for the next few lectures, we're going to talk about different types of data structures, different ways of storing data, and then of course operating on that data. And the reason why we want the language for talking about efficiency is we have to make decisions. We have to make decisions as to whether you use one data structure or another, and part of that will depend on the efficiency of the underlying data structure, the efficiency of the algorithms that operate on the data structure. And so we're going to dig in with talking about a variant of a list. A list, which is what you see here, is sort of the first data structure that we have used. Just a way of storing a number of elements that are presumably related to each other, and has lots of nice features. We're going to talk about those in a little bit. And we are going to, our second data structure, I guess now, is going to be a linked list. So it looks a lot like a list. It still stores data in these little cells here, but the lists are not connected in this sort of hard way. They have this loose connection, which I'm rendering with arrows. And so these boxes can move around a little bit. You can think about this, the difference between a bus and a train, with this being the cars of the train. You can make the train bigger or smaller by just attaching and detaching, whereas with a bus, the bus is the bus. There's no chopping it up into little pieces. So we're going to talk about linked lists and eventually doubly linked lists and a few variants on this, but here's the basic idea, is that we have this collection of data with this loose affiliation, which is going to have some advantages and disadvantages. But before we dive into this, we should really think a little bit more about the efficiency of various operations on a list. So we're going to do that first in this segment, and then in the next segment we'll actually start talking about linked lists, algorithms on linked lists, efficiency of the algorithms on the linked lists. So what are the types of things that we want to do with a list? We'd like to be able to insert things, search for things, and delete things, so sort of a standard operation. Okay, so let's talk about the runtime efficiency of doing something like inserting, if this is my list L with 9 elements, 0 to 8 in it, inserting at position 0 the number -1. So the notation here is L is the list, calling the insert function, at position 0, insert -1. All right, so what does it mean to insert a -1 here? I'm not replacing it, so it's not just L sub 0 equals -1. I want to insert it, which means all these elements have to slide over, and the -1 has to occupy that position. So it has to look something like this. I take 0 through 8 and I slide it over 1, so 0 is now at index 1, 1 is at index 2, and so on and so forth. I now have room in this 0th position to insert a -1, and there it is. So there's my new list. What's the runtime efficiency of this? All right, let's think it through a little bit. Well, let's see. Always have to ask the question, what are we measuring runtime efficiency with respect to? The length of the list. Obviously, let's say that that's n. So what did I have to do to insert at the beginning of the list? I had to slide everything over. How much time does that take to move the last element to the right one, the second to last element to the right one, and so on and so forth? Every one of those is an operation. So that is big O of n. So even something relatively simple like inserting at the front of the list requires everybody to move over. Let me go back to the bus analogy. Imagine you get on a bus and everybody's sitting in the seat, and you, because you're obnoxious, want the front seat, and everybody else being nice says, okay, fine. So the person in the front seat gets up and moves back one. That person moves up, get up, move back one, and everybody slides back one. That takes a lot of operations. N people had to get up and move over one at a time. Okay, so insertion at the front of the list, at least, is big O of n. Somewhat expensive. It's not logarithmic, it's not constant, but it's not exponential, it's not polynomial, it's not n squared. So linear in the size of the list. Good. What if we wanted to add something to the end of the list? So now you get on the bus, and instead of wanting to sit in the first seat, you're saying, I'm going to go all the way to the back of the bus, and I'm going to sit in the back seat. Well, that seems like it should be a little bit easier. So what happens if I want to append into a list the number 9? So I want a 9 sitting right there. Well, 0 through 8 stays put, so that shouldn't be quite as problematic, but there is no 9th spot here. There is no index here for that 9, so how do I do that? It seems like it might be O of 1 because everybody stays put and I've just got to tack on an element here, but that element doesn't exist, right? Once I have this list, that's the list. I can't index outside of it in the negative direction or in the outside the last element in the list. So what programming languages have to do, once you've created a list, in this case with 9 elements, and you want to append to it, it has to allocate new space for you. This space here in the X doesn't exist. So what it has to do is take these 9 elements, 0 through 8, take them out of this list that has only 9 slots in it, create a new list that has 10 slots in it for 0 to 9, and copy everything over, 0, 1, 2, 3, 4, 5, 6, 7, 8. Now you have an empty slot, shove the 9 in there, and that, of course, is still big O of n, because everybody has to get up and move on to a new bus. So it's as if you got onto a bus with only 9 seats in it. Somebody gets on the bus, they're like, all right, everybody off, get onto this new bus that has 1 extra seat in it, and then everybody can go on their way. So it's very expensive because you didn't have the space allocated to append. So even though it seemed easy at the beginning, turns out to actually be pretty expensive, still big O of n, whether you're doing it at the front or the end of the list. Now, because of that, Python is a little clever in how it allocates memory for you. So if I had a list with 9 elements in it, and I went to append in an element right there, Python wouldn't just give me 1 more cell, right? Because what if I then want to append 10 to it? Well, okay, now I got to take all of the elements off, put them into a new list, add 1 cell, do that. And if I'm doing that in a loop, for example, this is very, very expensive. So what Python says is that once you've appended, it allocates more space for you than you think you're going to need. So what that means is that although the list can only go up to here, this space is reserved on the off chance that you're going to append some more elements. And so that's just a programming language optimization, right? You don't have to do that, but Python does that. And what that means is that append at the end of the list, if the memory is there, can be O of 1, but it's sometimes O of n when you run out of space. Okay? So worst case scenario is big O of n. We have to admit that. But because the programming language can be optimized for us, and what it does, by the way, it doubles the size of the memory when you do an append and it's full. And so there's this bank of spaces for you. Now, there's an inefficiency downstream for that, which is you're taking up memory that you may not need. So we're giving up a little bit of overuse of memory for some runtime efficiency here for the appending. And notice again that this doesn't work for insert because insert has to move everything over. But for append, when you have extra memory, big O of 1. For append, when you don't have extra memory, still big O of n because everybody has to move into a bigger list. Okay, so that's insert at the front of the list, append at the end of the list. What about deleting an element? So what happens if I want to delete L sub 0? That's the del operator. All right, so it should be easy to delete this, but when I delete this, this 1 has to move over to here, 2 has to move here, 3 has to move here, and so on and so forth. Everybody has to slide back because once this is gone, this is now index 0, index 1, index 2. So that's going to cost me what? Big O of n again because everybody slid over. Notice, by the way, I've got a little extra spot here which will stay there per the previous slide where we can leave that extra memory there in case we want to append later on down the line. So delete, worst case scenario, is big O of n. If you delete the first item in the list, everybody's got to slide back down. What's the best case scenario? I delete the last element, and that's only big O of 1 because nobody has to move. So if I delete what's in the last element in the list, super cheap. But again, big O is worst case scenario. So worst case scenario is everybody's got to slide down. So insert, append, and delete are all big O of n, and append, with that one little exception, can occasionally be big O of 1 if you have allocated enough memory. Okay. So this is the delete of L sub 8. That, of course, is big O of 1. All right, so here is the summary so far. So we have a list, standard list that we've been using since 206A. Insertion at the beginning of a list is big O of n, right? And really, anywhere in the list is going to be big O of n. If I insert into the middle of the list, half of the elements have to move. That's n over 2. If I do n over 2 operations, what is the big O notation? big O of n. The multiplicative constants don't matter. So insertion is big O of n because we have to move things to make room for a new element. Append, I'm going to just special case this because sometimes it is big O of 1 if we have enough memory allocated for us, but sometimes it'll also be big O of n. Delete is big O of n because, again, best case scenario is big O of 1. You delete the last item, but the worst case scenario is somewhere in the middle or somewhere in the front. It's going to be big O of n. So it's a little costly. Is this bad? It depends. If your list is largely static, you just put a bunch of stuff in there and you're just accessing it, well then I don't really care if it's expensive to move things around a lot, add, append, and delete. But if the list is extremely dynamic and I'm constantly adding and removing and adding and removing, and the list is getting bigger and bigger and bigger, of course, well then this big O of n can start to be a little costly. Okay? So what is the last thing we want to do with lists, which is access? Right? We want to be able to find an element in the list. I want to be able to say, give me the 10th element in the list or the first element in the list. And by find, I don't mean search. That we've already done that. We know what the search algorithms are. That's the binary search and the linear search. What is access runtime? So if I want to reach in and grab the nth element in the list, what is the big O complexity of that? That big O is big O of 1. And the reason is that every cell of that list has a fixed memory size. So when I have to get to the 10th element, I don't have to count. I don't have to go to the first element and say, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I know where the 10th element is being stored because every one of those cells is exactly the same size in memory. And so I can just skip over the first 9 and index directly into the list at position 10, grab my element. So that right there is the big win with lists. Insertion and deletion and appending is a little costly. It is linear in the size of the list. But random access, accessing into a random position in the list, is extremely efficient because you know exactly where that item is being stored. So this is, in some ways, that trade-off. The list is rigid, right? All those blocks are locked together. So when I delete something or add something, everybody's got to move together. But that rigidity has a benefit, which is I know where everybody is, and I can access an individual element extremely efficiently. Okay? Good. So that's list. Insert, append, delete, access, big O of n, except access is big O of 1. That's the big win. So now what we're going to do is we're going to talk about linked list, and we're going to, first of all, talk about what a linked list is, how you build one. It's not built into Python for you. And then we're going to run through those algorithms again. Insert, append, delete, access, and we're going to compare and contrast. And again, it's not really a good or a bad thing. It's what do you need? Is your list dynamic or static? Are you doing a lot of accesses or very few accesses? So what is it that you want to do with your data? So it's important to understand that I'm not going to tell you this is your data structure. I'm going to say this is the data structure, these are the algorithms, this is the efficiency, and then you have to decide what your needs are in terms of what the data is you are representing. Okay, good. So when we come back, we're going to start talking about linked lists. I'll see you in a few minutes.